and all our online participants. We're now on the last lap of the meeting, but we saved the best part to the end with the session on framework materials, and we've got three of the best people in the world in this area. And our first speaker will be Bettina Lotsch. And I've known Bettina for 10 years, and I was asked by Claudia Felser if I would be her mentor when she was an up-and-coming young sort of tenure-tracked director at the Max Planck Lab in Stuttgart. And that was wonderful for me, and I don't know how it was for her, but it was wonderful to have that opportunity to spend a lot of time with her. Bettina's a professor in Munich, but also the director, one of the directors of the Max Planck Lab for Festkörperforschung in Stuttgart. And you have her CV in the program, so I'll simply not waste any more of her time and tell you she's going to talk about defects, disorder, and light storage in molecular frameworks for solar energy conversion and storage. Bettina.
Thank you very much, Tony, for this very charming introduction. And thanks to the organizers of this conference, Tony, Natalie, the board, for putting together such a wonderful program, and the invitation, of course, and also His Highness for his vision and support of this workshop all through the years. Okay, so let's get started. Now, you know, when we do morpho-COF chemistry, chemistry of molecular frameworks, we tend to live in a perfectly reticular world, a world of, you know, beautifully periodic nets without defects. But I guess, you know, we all know that this is only half of the story, because nothing is perfect, essentially. And also, if it were perfect, then probably it wouldn't be that exciting. You know, these materials might actually be quite boring. And this is because materials are not only known to host defects or to tolerate defects, but in fact, they can sort of impart functionality to these materials. And I just want to sort of highlight this by giving you three examples. So over here, NV centers in diamonds are highly sensitive quantum sensors for electrical magnetic fields. Defects in catalysis are often thought to be the actual active sites. And also when we look at solid electrolyte, superionic conductors, if it weren't for the defects like vacancies or also, you know, partly molten sublattices, most of them would be very, very bad ionic conductors. So in fact, I guess that gives you a rationale why we're interested in learning more about defects also in molecular solids. Although the defects in molecular solids might actually be quite different from defects in classical inorganic systems. Well, so let's take a closer look at the real structure of these molecular frameworks. And I'd like to, you know, going through the talk, I'd like to give you a couple of examples of very different types of real structure effects or defects and disorder in these materials. Now, to set the stage, let me introduce first the materials that we're going to talk about. So essentially, what we are going to talk about today are two-dimensional molecular frameworks, and you could consider them as heterographenes with holes. And so I'd like to start out with covalent organic frameworks. These are probably the most prototypical systems of molecular frameworks. And then towards the end, hopefully I'll get there, move towards carbon nitrides, which are closely related systems, also two-dimensional molecular frameworks that, however, have a much higher content, in fact, the highest possible nitrogen content, because they have backbones of strictly alternating nitrogen and carbon. So this is the maximum nitrogen content you can put in there, and that actually determines their special properties. I hope this is okay. It's a bit okay. Well, so why are we interested in these materials in the first place? So this is just sort of giving you a brief motivation why we tend to look at these systems. So basically, these are molecularly precise, heterogeneous systems that, you know, sort of deriving from graphene, and sort of, being heterogravhenes typically have a band gap. And that makes them attractive as systems for solar energy conversion, like photocatalysis or photovoltaics. And this is basically what we've been studying over the past couple of years, so very sort of different aspects of the photocatalytic activity in these systems. For example, the fact that we can move over from classical heterogeneous photocatalysts to all single-site heterogeneous catalytic systems when we replace, for example, the platinum co-catalysts in these systems by molecular catalysts. So that's not the sort of story of today, but I guess this motivation also shows you that defects in these systems can have quite dramatic consequences for the photocatalytic activity in these systems. And just to give you a couple of examples, so how can real structure effects affect photocatalysis? Well, for example, we can have changes in the optoelectronic or photophysical properties. For example, defects can, change charge carrier dynamics. For example, by introducing trap states that can lead to enhanced or delayed recombination. We can also have strain or stacking faults effect. We can, see poor blogging essentially by defects and so forth. But on the other hand, defects can also act as active sites. So I guess that tells you that defects in these systems can be ambivalent. So they can be good and bad essentially. And this, of course, motivates why we're interested to learn more about these defects and also where they come from and how they are formed. So let's first take a look at why these defects or how these defects form in these systems in the first place. So how are these materials made? Well, they are made by, let's say, a synthetic process that uses dynamic covalent chemistry. And so, the most important bit here is to understand why these systems can actually form in a crystalline way, why we can crystallize these molecular frameworks. Now, when you think about how do we install crystallinity in a material, then this is by using some sort of error correction mechanism, right? So we need to make sure that bond formation and bond breaking is essentially in equilibrium. So both can happen, and that the system then evolves into a thermodynamic equilibrium state, which is the crystalline state. And so this is not very straightforward if you think about it. It's not straightforward in an organic system with strong covalent bonds. So we have to use a trick, and this trick, as I said, is dynamic covalent chemistry. So for example, we use condensation reaction, where condensation and the back reaction, which is hydrolysis, are in equilibrium. So bonds are constantly formed and broken, and formed and broken. And so this then moves the system towards the thermodynamic equilibrium state. And that is actually very similar in carbon nitrides, although here we use actually solid gas reactions or ionothermal synthesis. I'll come back to this a little bit later. Okay, so just because there is a mechanism of error correction in place for the system doesn't mean that there are no defects or no errors. And so learning about these errors that typically are trapped kinetically here is actually quite challenging. And this is because we need a probe that has high resolution to really give us an idea what is happening locally. So we want to have a local view, and we want to have high resolution. And so TEM, electron microscopy, would be an ideal technique. However, that is challenging in these systems simply because they are so sensitive to the electron beam. Okay, so these are two examples that show you that nevertheless, we can use electron microscopy as a probe to study defects in these materials. And so this is actually an example that relies on the fact that we can use post-synthetic locking strategies of the imine bond. This is what we've done here, and I'll come back to that in a minute. And so what you can see actually from these examples is that in these materials we have rather small grain sizes. And remember, grain boundaries are defects, right? So we have frequent grain boundaries with grain sizes of a couple of 100 nanometers maximum. And so what we also see here is that when we zoom into the grain boundaries, we actually see that there's a covalent intergrowth. And that actually tells us a lot about the mechanism of formation in these systems, which we believe sort of goes through an amorphous gel-like intermediate that crystallizes with time and sort of pushes out the defects to the surface. And these grain boundaries are essentially the remnants of this amorphous state. Okay, so we can also see, for example, the origins of edge dislocations in these systems here. And interestingly, when you look at the connectivity of the building blocks in these materials, you'll see that we can only generate these 5- and 7-membered rings in these systems if we cross-connect, if the layers get cross-connected and we sort of introduce screw axes into the material. And that actually tells us that in these systems, you know, where we think these are two-dimensional systems, two-dimensional networks, these actually might be less two-dimensional and more three-dimensional than we actually think. And that can have tremendous impact on charge transport and charge carrier mobility in these materials. Okay, so coming back for 1 second to the mechanism of formation in these materials. So some of you might have noticed that there is actually a problem with the fact that we have to rely on reversible bond formation. And this problem is simple. If we want to allow reversible bond formation, we need to make, essentially by design, we need to make these systems prone to hydrolysis. So these systems easily fall apart in water simply because we're using reversible bonds. And that is, of course, a big challenge for using these materials in catalysis. So what we have to do here is we need post-synthetic locking strategies that ideally take maximum advantage of reversible bond formation in the first step, and then sort of in a second step, lock the reversible bond in place. And so this is a strategy that has been developed by many groups, including ours, over the last couple of years, and that gives you just a very rough overview of several strategies that have been developed for imine COFs. So post-synthetic locking strategies that involve either the linkage that is shown here in red, or that involve the building block and the linkage. And the most general of them are those here in gray, where we see that we can use these locking strategies at, you know, just about any unfunctionalized imine linkage that you can imagine. So these are very, very general locking strategies. Now, again, here is a bit of a catch, which is the fact that if we lock the system after reversible bond formation, the system, or the COF, is deactivated, typically. So it is more difficult to functionalize a post-synthetically locked COF. And functionalization is really something that we want in COFs. These are molecular systems after all, so we want to make, to install functionality there. And so this is what we call the COF trilemma. So essentially the challenge of making COFs that are crystalline, stable, and functional. So this is essentially what we want, right? And so how can we solve this trilemma? Well, I'll show you just, you know, very, very quickly one approach how we can overcome this COF trilemma. So this was a strategy developed by my PhD student, Lars Grunenberg. And so what he did is he started out from an amine and aldehyde building block, and in the first step made a typical imine system. An imine system that is not particularly stable to hydrolysis, and therefore can be hydrolyzed, and it's also a non-activated system. Now, in the second step, he used formic acid as the reducing agent, and so he translated the imine COF into an amine COF. Now, this, you know, the specialty of this amine COF is that it is a locked system. It's not prone to hydrolysis anymore, but at the same time, we've activated it because we can now add electrophiles to this amine function and introduce just about any electrophile directly to the linker group, to the linkage group. So essentially, we're ending up with both a functionalized and a locked system. So this is a very brief summary of what we have done. And this is basically a topotactic or topochemical process because we're using the Leuckart-Wallach reaction. So it's a very mild reducing procedure. And so we're ending up basically with crystalline, and that's important, with crystalline amine COFs here. Okay, so when we study this system in a bit more detail, we realized that it's actually much more versatile than we thought initially. And this is because we can not only make these amine COFs in a two-step process, but we can actually make them in a one-step process, starting directly from the building blocks and adding the acid, which then acts as both a reducing agent and a catalyst for COF formation. So that's a very simple procedure. What we can also do is we can use instead now ammonium formiate, do the same thing and reduce the system. However, in that case, we're introducing formal groups at the amine sites. And as a consequence, we're actually ending up with a disordered system. Now we can then, in a next step, we can go back and reoxidize the system. And so we can form mixed amine-imine systems. So we have mixed linkages here. And the interesting thing is that when we do this, we're actually ending up with a crystalline system again. So there's another layer of complexity here, which is the fact that we can actually switch between the different states of crystallinity, of order in these systems. And that might give us access to a more general sort of synthesis strategies for crystalline COFs. Now, of course, we want to know a bit more about what is going on in this material when we switch it between different states of crystallinity. So what does that actually mean if we have an amorphous COF? Does that mean the building blocks fall apart? Or is the principal connectivity still the same and we're just losing layer registry, for example? And so this is something that we've investigated with a structural probe that is actually quite insensitive to the state of crystallinity, but it's sensitive to atom pair distances. And this is pair distribution function analysis. And so, long story short, so here you see the PDF traces of different COFs that are either crystalline in green and blue or amorphous in red and sort of dark blue. And what you can see is that at small atom pair distances, these traces do not really differ. So they're essentially the same. And that means that at small distances, so neighboring atom distances that reflect the molecular level connectivity, these frameworks behave identical, so essentially the connectivity of the building blocks is identical and is preserved, right? Also in the amorphous state. And that's actually a quite important finding, I would say. Now, we also see that the damping at larger distances is much higher in these amorphous systems. And the loss of structural correlation at these larger distances is at the interlayer distance level and the pore level. So that essentially means that we have pore corrugations and interlayer shifting, and that then leads to the damping of these structural correlations. But the connectivity of the building blocks, and therefore I would say the intactness of the COF, is still preserved. And perhaps I should mention that this is actually, and we've supported this by calculation, so this is simply due to the fact that in these amorphous systems, and here we use partially formulated systems and also protonated amine systems, the conformational flexibility of the amine bond is much larger than that of the imine bond, and therefore we tend to lose structural correlations in these amine COFs much more than in imine COFs. Okay, so zooming out a bit, this is a summary of different mechanisms, how we can lose structural order in COFs. And so the most obvious of these sort of mechanisms is the one over here where we just simply dissolve the COF, right? So the building blocks fall apart, essentially, and that will, of course, lead to a loss of, long range, but also short range order. Another mode of crystallinity loss is that one over here that essentially corresponds to the one that I just showed you. So that is a loss of in-plane coherence that, further down the road can lead to total pore collapse. And that is due to increased conformational flexibility of the building blocks, for example. So here we're losing, porosity and partially, at least, structural correlations. Now, I would say the most subtle of these processes is the one down here, where we're only losing correlation along the stacking direction. So this is actually a mechanism of, or sort of a loss channel, right, where that is difficult to capture by any sort of structural technique or a structural probe. So let's take a closer look at this mechanism. So the mechanism of losing structural correlations along the stacking direction. So I think there is a general sense in the community that although we know a lot about 2 dimensions in COFs, right, the structural, the structure of COFs in 2 dimensions, we know only very little of the structure of COFs in 3 dimensions. And this is because it's simply very hard experimentally to say something about the stacking polytypes that we see in these materials. And so typically, COFs, when they are reported, they are typically reported as being ideally eclipsed stacked, right? Showing perfectly eclipsed stacking. And we know, and actually also that is supported from theory, we know that this is most likely the least energetically favorable case because of repulsive pi-pi interactions in these systems, or also Coulombic interactions. So although this is sort of the typical way in which COFs are portrayed, this is the least likely one. And so to study this and to learn where this discrepancy comes from and what it actually means, we selected a COF system, TTI COF, an imine COF, that is very unusual because it actually adopts 2 stacking polytypes. So this is the high temperature modification, which shows this very characteristic peak splitting of the 001 reflection. And then we have a low temperature modification that doesn't show this peak splitting. So it has apparently a higher symmetry. However, when you look at the local structure, the crystalline sizes, and also when you look at the Rietveld refinement, there's a lot of strain in this Rietveld refinement. So apparently, what we're seeing here are rather average structural effects, and effects that sort of do not represent the local structure of this material. So we resorted again to PDF, a technique that gives us more information on the local structure of this material. And so in a nutshell, you're now seeing here in purple the PDF of the high temperature modification. And I forgot to mention that the high temperature modification has a unilateral offset type stacking. So it's an ordered offset stacking that is sort of unidirectional. And then we have in green the PDF of the low temperature modification. And what we clearly see is that the PDF reproduces the experimental pattern quite well. So our model actually, represents the experimental pattern quite well. So we can assume that this is this unilateral offset type stacking is a correct assumption. Now we also see that for the low temperature system, the PDF is actually not at all well reproduced. So we see a lot of differences here. And so apparently our model is not correct. So we don't have an eclipse stacking. This is an oversimplification. Now it gets much better if we allow for unilateral layer offsets as in the high temperature modification. But this is still not a perfect match. Now the match gets, well, not perfect, but much better again if we allow these layer offsets to be random. And so that means that in this low temperature modification, we actually do have layer offsets, but we have random layer offsets. And these random layer offsets express themselves with a high apparent symmetry as an eclipse layer stacking would, right? So that makes sense. And when we now plug in this new model with the random layer offsets into our Rietveld refinement, including stacking fault simulations, then we see that the fit is actually much better now. So, as a sort of take-home message from this study, we've learned that in COFs that have an apparent high symmetry, the local symmetry is actually not described well by the eclipse layer stacking, but the local symmetry is actually much better described by random layer offsets. And that actually also has influence directly on the effective pore sizes in these systems. Because, you know, it's quite obvious if you shift the layers with respect to each other, the effective pore size gets smaller. And that can be important, for example, for catalysis, right? So our question was, can we actually do something about this? Can we control the layer stacking to an extent that we can sort of make sure that we maximize the pore size in these systems? And so my PhD student, Sebastian Emmerling, he actually had a very clever idea. And what he did is he thought, well, let's introduce some sort of anchor groups into the layers. And so these anchor groups, or the idea was to add interlayer interactions to the layers, right? And so sort of to keep the layers into place and make sure that the layers stack, well, not directly on top of each other, but close to eclipse, right? We never see eclipse stacking for the reasons that I discussed about, before. Now, okay, so what he did very quickly, he designed 2 series of COFs, so large pore COFs actually, very large pores, and introduced anchor groups, here denoted as R1 and R2. And so the building blocks just differ in the number of anchor groups that were added. So adding 1 anchor to each half linker, or 0 or 1 or 2 anchors. And so what we see directly in the powder patterns is actually that if we add these anchor groups, the crystallinity of the system increases. So that's very, very clear when you, so in both COF series actually. What we also see, and that is sort of directly, well, essentially what we wanted to see, we see that we can increase the pore size by adding the anchor group. So this is precisely what we had in mind. So increasing the effective pore size towards the theoretical pore size by adding these anchor groups. And what we also see from this, and this is sort of shown here in the matrix over there, there is a competition, essentially, between the interlayer interactions that we need to add and the pore size of the system. So the system tries to, or sort of tends to an offset, a staggered stacking, the larger the pore sizes get. And this is simply to minimize the vacuum, essentially, and to maximize the interlayer interaction. So the larger the pore sizes get, the more interlayer interactions, the more anchor groups we have to add to shift the layers back in place and make the pore sizes large, right? So this is basically shown here. And what I didn't show you is that by introducing these anchor groups, you're also increasing significantly the thermal stability of the system, for example. And of course, as I showed you, the crystallinity. Okay, so now the last example of this sort of part is, you know, from the realm of MOF chemistry. So the defect chemistry in MOFs is actually much more well understood. And Tony and many others have worked on that for years. But still, there are, let's say, blind spots. And so we actually got interested in these MOFs, porphyrin-linked zirconium MOFs, because we wanted to use them for catalysis. So many of the motivation, or much of our motivation, we sort of get from the possibility of using these systems in photo or photoelectrocatalysis. And so what we see here in the series of porphyrin-linked zirconium MOFs is that, you know, PCN221, MOF525, PCN224, all adopt a very similar cubic symmetry. Okay, I need to speed up. A very similar cubic symmetry, but they differ in a number of subtle or not so subtle details. And, you know, put very briefly, we have differences, for example, in the conformation of the linkers. We have differences in the linker content, and therefore the connectivity of the cluster. But importantly, we have differences in the cluster itself, so the zirconium oxo cluster. And you know, those of you like Mohammed working in the MOF field know that the zirconium-6 cluster is very ubiquitous in COFs, in MOF, sorry. But the zirconium-8 cluster is essentially non-existent. It only exists in very few MOFs, including this PCN221. So, okay, when we started working on these systems, we wanted to understand phase formation in these materials first, and we soon realized that, you know, the energy landscape in these systems and the phase space is so densely populated that reproducibility is a real pain in the neck in the system. So I'll pick out PCN221. So when we made this material, we saw a reasonably good agreement between the reported structure, or the reported XRD, and our XRD. So that was all fine. But then actually, we started making this material by starting from a zirconium-6 cluster, rather than a zirconium-8 cluster, or sort of making this zirconium-8 cluster in situ. And we ended up seeing exactly the same powder pattern. And that made us think, because this material is reported with a zirconium-8 cluster, and it's very unlikely that if you start with zirconium, a preformed zirconium-6 cluster, that this would dissolve during synthesis and sort of reform as zirconium-8. And in fact, when we do PDF, we see that, you know, the PDF is essentially identical with that of PCN224 that has a zirconium-6 cluster. And the match with the literature PDF of PCN221 is very bad. So that tells us that this material, in fact, has a zirconium-6 rather than a zirconium-8 cluster. Now, we were lucky enough to be able to grow single crystals of this material, and these single crystals consistently returned a zirconium-8 cube. So that really was, well, interesting, because we kind of knew that we have a zirconium-6 cluster. Now, when you look more closely, you'll see that we have a triangular electron density distribution in this thermal ellipsoid here. And this actually, this sort of triangular shape can be broken down in a superposition of 4 zirconium-6 clusters that are oriented in different directions, and they can be sort of transferred into each other by a 90-degree rotation. And that beautifully reconciles now the fact that, you know, one structural probe, the most averaging one, actually returns a zirconium-8 cube XRD, but all the local structural probes and also single crystal XRD is consistent with a zirconium-6 cluster. So this is what we find, and so we can now well, not reinvent the wheel, but we can now define a new structural model for the system that is actually very similar to PCN224. The only difference being the fact that the linker vacancies in these two systems, PCN224 and PCN221, is different. So we have disordered linker vacancies in PCN221, whereas we have ordered linker vacancies in PCN224. Now, in some of our XRDs, we see tiny little superstructure reflections that might indicate that indeed there might be nanodomains that are ordered also in PCN221. Okay, so with this, let me, in the last few minutes, I got that, Tony, thanks. Try to be very fast. Okay, so try to switch over for the last couple of minutes to carbon nitrides, which are closely related to COFs, as I just mentioned. And in fact, this is a class of materials that has been around for a very long time. In fact, you know, many of the famous chemists back in the days in the 19th century, Liebig, Wöhler, Berzelius, they all worked on carbon nitrides. And Liebig is the one to blame for these very unintuitive names that he gave them, like melamine and melem and melon. And so this is, you know, he gave them, and this is actually what you can or cannot read in German here. So basically, Liebig, you know, said, well, I just call this material melon simply because I like the name. There's essentially no reason for it. Okay, so typically these materials are made from very simple precursors. So they are dirt cheap to make. So you can use urea and end up with melon if you thermally treat it. And this is a thermal condensation reaction. So this is essentially a gas-solid reaction. Now, we realized a couple of years ago that when we make these materials by ionothermal synthesis, so in a salt melt, we can actually get truly two-dimensional carbon nitrides. And the carbon nitride that I would like to talk about in the very few last minutes is potassium PHI. So polyheptacene imide. So this is a very special carbon nitride, and luckily it is a crystalline carbon nitride, so we know quite well how it looks like, both on a local and long-range structural level. So we've done a sort of comprehensive study that tells us that, you know, we do not just have a two-dimensional backbone, but in this backbone we have hydrated alkali metal ions. So we have alkali metal ions and water in the pores, and they are actually structure directing, so they direct the layer stacking. Now, what we also saw, and this is quite interesting, is that although the band gap between the one-dimensional melon and kPHI is actually the same, we see a much higher photocatalytic activity in kPHI, much higher, factor of almost 20. And you know, we then found out that this is due to the fact that on photoexcitation of this material, the holes are extracted very quickly, and the system gets photo-reduced and forms a radical anion. And this radical anion is extremely stable. It changes its color to blue, and this blue radical state is persistent if you exclude oxygen for hours. And we also found, and these are actually pretty recent results, we found that the fact that alkali metal ions are hosted in the pores are actually at the heart of this high stability of the radical anion. So there must be an interaction between the intercalated metal ions and the electrons that are trapped on the material. And so to make this a bit clearer, what happens here is that this is now our current understanding. We form a an exciton. The holes are quenched very quickly, so the whole transfer reactivity is very high in these systems. So they are quenched by a sacrificial electron donor, and the electrons actually stay on the material and get screened by the mobile. And I should say that these ions, we could show they are mobile. That's important. So they are screened by these mobile ions in the pores. And so, so what we believe happens is essentially a screening of the light-induced electrons on the materials by the mobile cations in the pores. So, if you will, there is a coupling between light-induced electronic charge carriers and ionic charge carriers. And so that is a good example for an optoionic material. We actually call this process light storage. That's a bit simplified, perhaps. And the mechanism by which this happens is actually known for a very long time. I tried to speed up, Tony. Known for a very long time, and was described in the 1980s by Tribuc already. So he gave it the name photointercalation. And he showed actually that this works for P-type transition metal dihydrogenide. But meanwhile, it has also been shown for N-type oxides like molybdenum trioxides. And we believe that this process is actually also at the heart of this charge carrier stabilization in PHI, where there's a direct connection to the electrolyte. And so ions from the electrolyte are attracted into the material and sort of then screen the light-induced electronic charge carriers. Okay, and you know, so I'll skip some of the slides. I'll move on to... He said it's okay. That's great. Thank you, Mohammed. But I'll still I'll speed up. Sorry for that. Okay, so to more or less, you know, this is a kind of summary slide. I'm not quite at the end, but quickly. So so what we did is we tried to develop different schemes where we can actually combine this light absorption and photocatalysis or photocatalytic activity of PHI with its charge storage properties. And so we developed the concept of dark photocatalysis, where we separate essentially the light reaction from the dark reaction. We developed photoresistive sensors, solar batteries, and you know, the one application, I'm skipping this one here, that I would like to show you at the end is the solar battery swimming. Let me just very briefly, explain that to you, because it also, in a sense, includes the dark photocatalytic or dark photocatalysis application. So essentially, you know, to set the stage, colloids can be propelled by inducing asymmetric reactions around their surface, which lead to a concentration gradient of solute species across their surface. And that is actually a process that is known, this propulsion process known as self-diffusiophoresis. Now, if there's an internal charge transfer involved, this is known as self-electrophoresis. And if we now use photocatalytic reaction to induce or as the surface reactions, then we can create light-driven microswimmers. And so we were curious to see if we can actually do this with PHI. And so we teamed up with our colleagues in the Metin City department at the Max Planck Institute for Intelligent Systems. And we created PHI Janus particles, which are capped by a metal. So we have made them asymmetric. And you know, now we wanted to see if by adding a donor and using their photocatalytic reactivity, we can propel these particles in solution. And so this is exactly what happens. So here you see a video where we use 5% methanol as the fuel. So this fuel is photocatalytically degraded. There are actually competing reactions at both the platinum cap side and the PHI side. And we can also use different donors, like, for example, 4-MBA. So in a nutshell, what we see, the particles can be propelled by different fuels, including actually fuels like glucose. So we can move the particles with very benign fuels. Now, so finally, we were interested to see if we can create some very sort of new type of motion by using a specific combination of cap and fuel that allows us to track or trap charges on the particle. So charge trapping that I just sort of showed you happens in PHI. So use charge trapping to turn off the light and then propel the particle in the dark. So this is something we call solar battery swimming. So can we do this with PHI? And in a nutshell, this works for PHI if and only if we combine H2O2 as a fuel and use a platinum cap. And then what happens is that, you know, using both reactions at both sides of the sphere on PHI and platinum, we can charge up the particle in the light, and then we turn off the light, and the particle slowly discharges and keeps on moving. And so to show you that this really happens, here you see what happens when the UV light is off. So the particle just shows Brownian motion. And then we turn on the light, watch, and now it picks up speed and swims, and then we turn off the light, and then you see it just continues to swim. And this is actually seen even better here, where the light is on and off right now, and we see that the charge decay goes on and on and on. And I'm essentially done. So you see that this charge decay, okay, let me just go to the final slide. So essentially, I'm sorry. So essentially, you can see that if we charge the particle up for 30 seconds, it goes on for 30 minutes and swims in the dark for 30 minutes. And so this essentially, I'll stop here. That was the last slide. That was the last sort of meaningful slide, yeah. Okay, I'll skip over those. That is the last meaningful slide because it shows the people who have done the work, essentially. So that is my group, thanks to these young, motivated people, without whom this wouldn't have been possible, obviously. And thanks also to the funding agencies. And thank you for your kind attention in spite of running over time. Thanks, Mohammed.
Thank you, Bettina. It's a wonderful talk. Do we have any questions online, Natalie? In which case, do we have questions from the room? I do have a question. Oh, yeah, Vinay.
Fascinating. I really enjoyed it. A lot of your work reminded me of turbostratic graphite and those kinds of materials. So do you gain inspiration, or do you use some of those techniques that look like PDF, et cetera, very similar problems as in graphite?
Yeah, that's a very good point. I mean, and you know, essentially, turbostratic graphite that also shows rotational disorder of the layers is a very similar system indeed. You know, turbostratic graphite, of course, has been used a lot to exfoliate graphite, also into graphene, but you know, long story short, I'm sure that local probes have been used on that material as well, and so the basic mechanisms also of loss of coherence are clearly the same. So yeah, it's a very closely. Yeah, well, it is a closely related materials. Of course, there are differences, that's for sure, but by and large, very similar. Thank you.
I had a quick question. It requires a quick answer. With the COFs, when you put these anchors in to keep them aligned, can you also control the spacing?
That is a very good question, Tony. So, in principle, you can control, or let's say, you know, the bulkiness of such anchors would have an impact on the stacking. That's for sure. Typically, you see this impact simply by a broadening of the stacking reflection and a loss of coherence. So, you know, it's challenging to make this sort of into a design concept, because if you pry the layers apart, you also need to make sure that you're not sort of losing coherence and exfoliate your material completely. So I think it's tricky, but it's certainly something that can be done if you choose a clever sort of linker design and anchor design. Yeah.
Well, let's thank Bettina again for a wonderful talk.